Hello, and welcome to Shapes and Molecular Polarity with Dr. Kim. What we're going to do now is take the Lewis dot structures that we drew in another video and determine the shape of those molecules and determine if the molecule is polar or not overall. Our first example is SeCl2. Previously, we drew the Lewis dot structure and got this. What we're going to do now is figure out the shape of this molecule. You will need to have your Chem 130 shapes table in front of you. Looks like this. To figure out a shape, we're going to figure out a generic formula for the molecule. A is the center atom, B are other atoms connected to the center, and E's are lone pairs connected to the center. So in other words, we're interested in these lone pairs connected to the center atom, whereas we're not concerned about the lone pairs on the outer atoms. They don't change the shape. So we have a center atom, which is A. We have two atoms connected to the center. We're going to call those B's, and there's two of them, so AB2. But don't forget we have two lone pairs bonded to the center atom. So that counts as E2, AB2E2. Let's go to our shapes table and find AB2E2. It's the last one. It should look something like this. A center atom with two bonded atoms and two lone pairs. Does that look familiar? Yes, it does. The name of this shape for AB2E2 is bent, meaning the atoms are not in a straight line. And the bond angle is less than 109.5. So the shape equals the fancy name of bent. Where'd they get that anyway? That's some really scientific term, huh? Gee, it's not in a straight line. Oh, it's bent, duh. So, bent is the name of the shape. And again, the bond angle is less than 109.5. So we get all that information from our table. Now let's look at the polarity. We've already talked about polar and nonpolar bonds in a video, which I hope you've already watched. If you hadn't, you really need to watch that first. So let's look at the bonds we have in this molecule. We have Se to Cl bonds. Se to Cl. So let's determine if these bonds are polar or nonpolar. Here's Se and here's Cl. Who's closer to F? Cl is closer to F. This makes the Cl a little bit minus, and the Se is then a little bit plus. So we can draw an arrow pointing towards the Cl and cross the positive. So in my molecule, on scratch paper, we can draw arrows along the bonds pointing towards the Cls. So we have two arrows, and then we have these two lone pairs. Now, for the whole molecule, we have to determine if the arrows are going to cancel out or not. That's how we determine the polarity for the whole molecule. We look at the arrows. Okay, these arrows looks like they do not cancel out because they're not equal and opposite. So, while we have polar bonds, the polar bonds don't cancel, which means the molecule is still polar. It is a polar molecule as well. It is not symmetrical, so the bonds don't cancel, meaning it's still polar. So this molecule still has a negative side and a positive side. It's a polar molecule because the polar bonds do not cancel out. Let's look at another example. Earlier, we did the Lewis dot structure for HCN, and this is what we came up with. Let's figure out the shape. We have a center atom, C. We have two atoms connected to C. There are no lone pairs on the center atom C. Again, we don't care about the lone pair on the B atom. We only care about lone pairs on the center atom, and there are not any, so it is AB2. Let's find AB2 in our chart. It's the first one. It shows a center atom with two atoms attached to it and no lone pairs on the center atom. However, it shows it linear. We drew our Lewis dot structure bent. So actually, as far as shape goes, it would have been better to draw this in a straight line. It doesn't mean the Lewis dot structure is wrong, but this one is better because it more clearly reflects the shape. The shape of a straight line is, of course, linear, and the bond angle is 180 degrees. So HCN is actually a linear molecule, and the bond angle is 180 degrees. Why do you think this is linear in the first place? Why isn't it bent? Well, electrons are negatively charged. And there's electrons in this bond here, and there's electrons in these bonds here. And they're going to want to get away from each other. So we're going to push apart. And the farthest we can get these bonds away from each other is, in fact, 180 degrees. So they're going to push apart to where they're the farthest away they can. So electrons repel. This is important to remember. That's why we have the shapes we do. So as a side note, I'd like you to remember that electrons repel and push away from each other. And that's why this would be linear instead. Now let's talk about polarity. We have an HC bond and we have a CN bond. Those are the two bonds in this structure. What do we know about the HC bond? Would that be polar or nonpolar? I hope you remember from your lesson that CH bonds are nonpolar. What about C to N? Well, if we look at our periodic table, we see N is closer to fluorine than C. So N is actually going to be a little bit negative. C is a little bit positive. This bond is in fact polar. So we can draw an arrow pointing from the C to the N across the C. So we have one arrow. There's nothing to cancel out with it. So the molecule, do you think it's polar or nonpolar since we only have one arrow? Well, without anything to cancel out with it, it stays polar. So our molecule is polar as well. All right, I hope this has helped you to determine shapes and polarity of molecules. Good luck.